Anybody have any like burning questions about the exam that's been bothering them since Tuesday? No? Okay. Number 2. Oh, shoot. Let's see. Let me just, yeah, maybe I'll just say something about it now. And, okay, number 2. Yeah. Uh, okay. Yeah. So you have a tank and you know the volume, and it's filled with steam. So it's filled with a gas. And as stuff's leaking out, um, a gas will just keep expanding to fill whatever, uh, you know, that from farting, you know. So it'll take up all the space in the room if you give it time. Um, so this tank, as steam's leaking out of the tank, whatever mass is left in there is spread out over that full volume. So you know the volume of the gas the whole time is the idea. And so then you can use the fact that when you know, let's see, uh, so the total volume is equal to the mass times the specific volume. And you know this the whole time. At every instant, this is 1.5 cubic meters. And so when you lose a bunch of that volume, you know the mass, and you know the total volume, so you can calculate the specific volume. And then and you're given the temperature. So then with the temperature, use the temperature and the specific volume to look up the pressure in the table. So that's how that works. And I think with the numbers I chose, it worked out to be an exact, so you didn't have to interpolate or anything. Any other questions about that one? Yeah, sure. Anything else about the test real quick? Otherwise, we can go through the problems as much as you want on Tuesday. Yeah. On that one? Oh. Oh, yeah. So there's the integral stuff. Yeah, so you have, so the equation you have is that dm dt in the control volume is equal to negative 0.2, and this is before you do the integral, so it's just negative 0.2, and then you can separate variables, and you get dm in the control volume is equal to, negative 0.2 times the integral of dt. Well, if you take the integral. Key thing here is, so our time, we're going to go from 0 to t, and the t in here is a dummy variable. Over here, now remember that we're not, when you do this integral, if you do it as a definite integral, you're not using the same boundaries here as here. You're using the two same instants. So, so this one is going from state 1 to state 2. And so you have to think about what, when you integrate this, you're going to get the mass in the control volume. You have to think about what the mass in the control volume is at those two states. So this would be I don't remember what the, okay. So this is going to be integrating from 3.22 to 1 point, you guys have good memories, 1.04. And that's equal to, and now you can, you can also just do it as, you can just think of it as the integral from state 1 to state 2 of dm is just equal to the change in the mass. So if you just, so you can forget the sort of fiddly stuff, you know, avoid the fiddly stuff with the bounds of integration and just think of what's the change in mass that you need to satisfy the requirements, and then set that equal to your definite integral. Both of those two ways work. So that change in mass then would be 1.04 minus 3.22. You can see it comes out the same, you know. And so the change in m has to be negative, and then set that equal to the other. Any other questions? Yep. Yeah. Oh, yeah. I wouldn't take off any points for that, but it would have put you at a place in the table where they're most likely you would have to interpolate. So it would cost you a little time. Yeah, so so I wouldn't take off any points for that. Any other questions? Okay. Any homework questions? Okay. And then I didn't look before I came to class, but is Tuesday the day you're bringing your binders in? Anyone remember? It must be coming up soon, I think. Oh, is it? Okay. Is that the last day of class? Okay. Okay. I wonder why I did it that way. Okay. Well, leave that alone for now. What if I actually, what if I did this? I think, what if I said, um, so that you have your binders back as we get closer to the final and stuff. What if I said anytime, like you can bring it in anytime starting next Tuesday. The sooner you get it in, the sooner I'll get it back to you. Okay. So, but if you need that extra time, feel free to take it. But I'll do the second binder check. So the second binder check, open turn-in period. Is going to be Tuesday. Oh, that's okay. That's Thanksgiving. That's the class before Thanksgiving. Oh, the last quiz. So there's a quiz. Okay, forget this. This is dumb. Okay, let's just do it December 6th, and I'll get them back to you right away. Okay. All right, so now we're going back to the second law of thermodynamics. Um, And I want to sort of map out the thought process that we're going to follow for this. And there's kind of going to be a lot of talking. By the end of class today, I think we'll get to some simple equations and stuff, but I don't think there's really any way around me just spending a lot of time writing stuff down and describing relationships. But first, let me give you sort of a roadmap so that you have how it all fits together in mind. I think all this stuff, so I'm going to give you the thought process of how you get from one thing to the other. I'm not going to go through any of the mathematical proofs, although that's sort of like the heart of it is there's mathematical proofs between all these things. I'm not going to go through that, but I want to just map out how you go from step to step, kind of. So the first step for the second law of thermodynamics is the one that seems obvious. This is like, if you had lived a long time ago, you could have thought of the second law of thermodynamics. So the starting point is that heat transfers spontaneously from hot to cold. That's super intuitive, and the fact that we're going to eventually get from this starting point to math that's going to be super useful, that there's no other way to get to, is kind of amazing. So this is very intuitive. And this is called the Clausius statement of the second law. Starting at that point, you can prove mathematically, and I'm not going to outline the proof. I'm not going to go through it. But there's a math proof that's not horribly long or anything that Clausius statement is equivalent to the fact that, so in words, I think the easiest way to think about this is not all the heat input to a heat engine. By the way, a heat engine is the same thing as a power cycle. So not all the heat that's input to a heat engine can be used as work. Some of that heat is lost as exhaust, and there's no way to change that. This can be written mathematically so that first, the first one, the sort of sentence form, is sort of how it makes sense to me intuitively. But you can write this mathematically by saying Um, for a system in contact with one reservoir, one thermal reservoir, the work done for any cycle that that system goes through is less than or equal to 0. Okay, so you can think of it as this, or you should keep both of these in mind. This is the sort of intuitive one. This is the Clausius statement. And how do those work together? Well, the idea is if you don't have any of your energy lost to the exhaust, okay, exhaust is lost to a second thermal reservoir. Normally for a heat engine, you'd have a high temperature reservoir that the heat's coming in. That's the coal you're shoveling into the fire to make the engine go. Then you have a cold reservoir that the exhaust goes to. If you don't have that cold reservoir, then your system is connected, or if no energy is going to it, then you can think of that as like your system is connected to only one thermal reservoir. It's not using any cold. It's not making any use of a cold reservoir. So that's a one reservoir system. And if you don't need energy to go to the exhaust, then what you'd have is a heat engine, a power cycle, where energy is coming in at the boiler and all of it's being used for work. Well, that can't happen. Some has to go to this second cold reservoir. Anyone remember what this one's called? What's the second statement? Kelvin-Planck. Yep. Kelvin-Planck statement. This is what we're going to be talking about for the rest of class today. And it turns out that this statement is going to be really useful for evaluating the performance of three important cycles. Power cycles, that's the one where you input energy as heat from a boiler and you use that to do work. That's your goal, is to do work. Refrigeration cycles, and heat pump cycles. Okay, so we started with, yes. These two statements are so these two here are just two different ways of thinking about the Kelvin-Planck statement of the second law of thermodynamics. We started with the fact that heat spontaneously only goes from hotter to colder. We use that to sort of reassert the second law as the Kelvin-Planck statement, which has uses for performance of different kinds of cycles. Step 3 is another just mathematical equivalent. So there's another math proof that we're going to skip, but again, these are all just mathematical equivalences that says the Kelvin-Planck statement is equivalent to what's called the Clausius inequality. Or yeah. And then this that uses some things that I haven't talked about yet, so I'll leave that aside for now. And then the last step is that the Clausius inequality leads to the entropy statement of the second law. So this idea of entropy, which is, you've probably heard several people, including me, talk about entropy as sort of this sort of loose idea of disorder. And I said that entropy is sort of a measure of how useless the energy you have is for producing work, how hard it is to use it to produce work. But entropy is something you can calculate. It's a property. Any material has an amount of entropy that can be calculated. And where did that idea of this sort of strange combination of things that we call entropy, where did it come from? It comes from this Clausius inequality. So I think as you're thinking about this, keep this set of steps in mind. Okay. It'll sort of help keep you centered on where all this is going. Any questions before I go on to talking about the Kelvin-Planck statement? Yeah. 2 and 3. Good point. There's a Clausius statement of the second law of thermodynamics, and that's a very different thing than the Clausius inequality. Like I said, if you lived a long time ago, you could have come up with the Clausius statement, but they probably wouldn't have named it after you. They would have named it after somebody who did a lot more cool stuff than just that, like this guy Clausius, who came up with that sort of obvious fact in a body of work that went a lot farther. So, the Clausius inequality is kind of the first thinking about this this property of entropy. Okay, so there's not really much to say about step 1. The Clausius statement, the fact that heat goes from a hot to a cold. So today we're going to talk about the Kelvin-Planck statement. Of the second law. Okay, so what does this say? So here's a general diagram of a heat engine, of a power cycle. So that's the system. Up here we have a thermal reservoir. That's the high temperature one. Down here we have a thermal reservoir that's cold. And heat comes in from the hot thermal reservoir. I'm going to call that Q sub H, the heat coming from the hot reservoir. And so that's energy coming into the system. And energy leaves the system in two places. Energy leaves as work. That's the one we want. And then the one that mathematically we just know we can't avoid, that's the energy that's leaving in the exhaust. And I'll call that Q sub C. And the Kelvin-Planck statement says Q sub C can't be equal to 0. You can't get all the heat to just be transferred out as work. Like I said, this is going to be we'll use this to establish like not just this is sort of philosophical or whatever, but we're going to use this to establish practically useful mathematical limits on the performance of three types of cycles. Let's see. So on the performance of, and these three cycles are heat engines, and I just drew that diagram. That's the same thing as a power cycle. So the diagram is above. Refrigeration cycles and a diagram of a refrigeration cycle looks like this. If this is the system, and there are two reservoirs again. The top one is the hot reservoir. The bottom one is the cold reservoir. Okay, so how does a refrigeration cycle work? So in a refrigeration cycle, what you're trying to do, your goal with a refrigeration cycle is to take energy out of the reservoir that's already cold. So there's your Q sub C. Where do you want to put that energy that you take out of the cold? You want to put it in a hotter place. That's the challenge of a refrigeration cycle. You want to pull energy out of where your vegetables are and deposit it in the room or outside your house or whatever. Same thing with air conditioners. And so you want to remove this heat, Q sub H. And there's no way to do that by itself. If this was all you were doing, that would violate the simplest form of the second law of thermodynamics that says you can't spontaneously just move heat energy from cold to hot. And so you have to put energy in as work. Okay, so this is where your vegetables are. And then the third type of cycle is a heat pump cycle. So what does the diagram look like for that? Here's your system. You have two reservoirs again, the hot reservoir and the cold reservoir. This time, goal with the heat pump. You're trying to take your region that's already a higher temperature, your hot reservoir, and put more heat energy in there to raise the temperature. So there's your Q sub H. Well, where are you going to get that heat energy? What you want to do is you want to take it out of a lower temperature region. So like if you're talking about a heat pump that you use to heat the inside of an RV or something, you want to take the heat energy, the thermal energy that's outside where it's cold, force it into your inside that's already warmer. That's your QC. And again, you can't do this by itself, and so you need to do work to get that done. And so here, the idea is the people who are trying to stay warm are in that hot reservoir, and you want to warm that up. Notice that these two, the heat pump and the refrigeration cycle, are the exact same thing. The only difference is what reservoir is the place that you care about. And like if you turned your refrigerator around backwards, you could sit next to the coils and it would work as a heat pump for you at the same time as it's cooling down your vegetables. Okay, it's the same thing, it's just what reservoir matters to you. Here are a couple things to notice. So first is what I just said, the refrigeration and heat pump cycles are the same exact cycle. It's just a matter of which reservoir you care about. Also notice that, that it is, in both cases, reservoirs that you care about. If you're talking about, so if you're doing calculations involving a refrigerator or freezer or an air conditioner or refrigeration cycle, your system is going to be the refrigerant that's moving around through the tubes in your refrigerator. Your system is not going to be the inside of the refrigerator. That's a reservoir. Okay, that's the cold reservoir. Same thing with the heat pump cycle. Your system is going to be the refrigerant, but you care about the reservoir. And then the second thing to notice is that the refrigeration and heat pump are exactly the reverse of the power cycle. So look at one of these. Look at this refrigeration cycle. You have heat energy going to the hot reservoir from the system, heat energy coming into the system from the cold, and work being done by the surroundings. Each one of those is reversed in the power cycle. So in a power cycle, you're taking heat energy from the hot reservoir, spitting it out to the cold reservoir, and doing work in the process. Okay, I think that's it about that. So we're going to start with this mathematical form of the Kelvin-Planck statement of the second law. And this mathematical form says for a system. Oh, I know what I was, sorry. One thing I want to say about this before I go on. So notice that the directions of these arrows are telling you what would be a positive value of QH, QC, and W in each one of these cases. Okay, so it's not going along with our first law sign convention, but this would all be like when we're talking about a power cycle, if I use the term QH, that's a positive amount of energy going to the system. If I talk about a QC, that's a positive amount of energy leaving the system. Work, you know what I mean? So these are all going to be positive in each one of these cases. Okay, so the mathematical form of the Kelvin-Planck statement for a system with a single let me be more careful about this. For a system in contact, so the thermal reservoir isn't inside the system. The work done in any cycle that system goes through, and the fact that it is a cycle is important, has to be less than or equal to 0. Okay, so this W is work done on the surroundings by the system. Okay, so if you have the most efficient possible system that you're trying to use as a heat cycle, okay, the most efficient it can possibly be is that if you have a single thermal reservoir, you can get that. Well, I guess that's not really a very good way to think about it. So if you have a efficient system in contact with one thermal reservoir, and you're able to do 0 work and not require any work to come into the system, the only way to do that is that there's no heat coming in from the reservoir. There's nothing you can do except absorb work energy. And we can think of splitting this up into 2 different cases. The equality, and the equality, so, we're saying that for a cycle with a single thermal reservoir, the work done by the system is equal to zero. That's the equality. So the work done over a cycle is equal to zero. The system is perfectly efficient in some way. And so we're going to talk a little bit about what that means. What does it mean for it to be perfectly efficient? Well, we've used idealizations like this a lot in mechanics. I mean, not in this class, but in your other classes. You know, you're always making assumptions of no friction, no air resistance. When you took physics 2, you know that for perfect efficiency of a system, you can't have any resistance in the cables. Otherwise, you're just throwing energy away in some sense. So think of this as no, for now, no friction, etc. Okay. And then the second is the inequality. And the inequality says that the work done by the cycle is less than zero if there are inefficiencies. So what are these inefficiencies that we're talking about? Well, think about like a mechanics example. Think about a pendulum. Okay, so air resistance or friction, then one thing you can say about this system is that in some amount of time, it can return back to its starting point, its starting state. So the system and its surroundings can return to its starting state. You know, that's what an ideal pendulum does. It keeps returning to its starting state once every period. What if you did have friction and or air resistance? What would happen? Well, then if you just let it run, each time it would be a little bit lower until it stopped, right? You could return the system to its starting state, but you couldn't return the surroundings to the starting state. You'd have to require that the surroundings do something to it to return it to its starting state. Like you could put a little motor in here, you know, or do something with your hands. But if you, with your hand, return it to its starting state, you're a little bit hungrier after that. You've burned up a little bit of energy doing that. You know what I mean? And so this idea of the system being able to return to its starting state is kind of a way to think of these inefficiencies. We're going to give that a name now because friction and air resistance is only one category of the things that we have to worry about. We're going to call it reversible. Okay. Um, yes. Thank you. Okay, so so if you have no friction, no air resistance, that system is reversible. That's what we're going to call it. Um, it's the same thing with, I guess you could have two capacitors, start with a whole bunch of electrical energy inside a capacitor. There's another capacitor on the other side, and energy would discharge from one capacitor to the other one, and it would oscillate back and forth. That's what would happen, right? Seems like it would. That's a reversible system until you put, until there's resistance in the wires, or you put resistors in there. Then little by little, energy is being lost, and eventually that system will stop. You know, there won't be any more current flow. So that's where the idea of like a reversible system comes from. And the things that keep a system or a process from being reversible are called irreversibilities. And this idea works as well in mechanics and electricity as it does in thermodynamics. You know, you're just not used to calling it that, but you know, it's just sort of a new name for a bigger category that includes these things that you've dealt with before. And here's the list of the things that we're going to consider irreversibilities. And there are 7 of these things. The first one, friction and air resistance, I'm going to call that a single category. The second one is electric current through a resistance. Um, the third one, which maybe you've possibly talked about sort of in passing in a class before, but it's connected to mechanics. So it's sort of an idea that, you know, you could have dealt with before, is inelastic deformation. Okay. Elastic deformation. Well, what is elastic? Okay, so I think that's what most people think of it, but in a way, it's what follows the stretchability that makes something elastic. The idea of elastic. So, like, what makes a good elastic waistband? Yes, that's so. The key thing to being elastic isn't that you can stretch it to put it on. It's that then when you let go of it, it returns to the size of your waist and keeps your pants up. Okay. So something that's elastic, when you return the load, it returns to its shape. Okay. So if you apply a force to something elastic, like a slingshot, you know, you put energy into it to pull it back. When you let go of that, and now all the energy is in the elastic and it's applied to the thing. So in that sense, an elastic object, when you deform it, no energy is lost. That energy is just stored there until you let it return to its shape. Something that's inelastic, something like if you crush a can, an aluminum can, you crush it, remove the load, and it stays crushed. Okay, so the energy that you put into crushing it is gone. Okay, that's an irreversibility, and that's why that appears here. All of these things are, and you're more familiar with these first three, but the idea with all of these is that you put energy into it, and that energy is gone forever. There's no way to get it out. That's the way it is with friction. You know, like you slam on the brakes, your tires skid, there's friction. There's no way you can use that again. You know, it's gone. Okay, so now the new ones. Number 4 is heat transfer through a finite temperature difference. Yeah. Um, so if you have uh, some material that's 100 degrees and some material that's 20 degrees, and you put them next to each other in thermal contact, you know, or with a with like an iron barrier between, so heat can transfer from one to the other. Heat's going to go from the high temperature one to the low temperature one. Since that's a finite temperature difference, there's no way for that system to spontaneously reverse itself, right? It's irreversible. Once that heat goes that way, that's the end. You can't do any more with it. So the only way to have a perfectly efficient transfer of heat is to have an infinitesimal difference between those two temperatures. And how long would it take? Like if they're both, this one's 70.000001 degrees and this is 69.99999 degrees, how long is it going to take for any finite amount of heat to transfer? Infinitely long. So it's not really a practical thing, but none of these are practical. You know, you can reduce a lot of these pretty low, but there's no such thing as eliminating any of these. And so this is again, it's an idealization. But if you want perfectly efficient transfer of heat, it needs to be an infinitesimal temperature difference between the two things. The fifth one is unrestrained expansion of a gas. In order for that to be a reversible process, so for a reversible expansion of a gas, the gas must be in equilibrium at each instant. You know, we've used that quasi-equilibrium idea before. It's sort of the idea here. Again, like how long would it take to let a gas expand where at each instant it's in equilibrium? Again, it takes infinitely long. I mean, you can't move if you're always at equilibrium, you know, but it's an idealization. Number 6 is chemical reactions. Yes. Yeah, quasi-equilibrium means it's going slowly enough that you're basically in equilibrium all the time. So that means that if you're treating a process as quasi-equilibrium, like with an ideal gas, for example, it means that you can use the ideal gas law at any instant. Okay, it's going slowly enough that that's a reasonable assumption. If you're doing some fast process, like a gas a gas comes into the room and is expanding quickly, you'll get wrong answers if you use the ideal gas law while it's expanding. And then the last one is mixing of materials in different states. And you need to keep all of these in mind as you're going through problems so that you can identify places where there are irreversibilities. These are all the things that make your system less efficient. Okay. So back to the Kelvin-Planck statement, the mathematical Kelvin-Planck statement. If your system has no irreversibilities, and remember this system is still in contact with a single thermal reservoir, then the work done by a cycle is equal to 0. If your system has irreversibilities, then your work done over any cycle is less than 0. So in both of these cases, we're talking about a system in contact with one thermal reservoir. Okay, now this idea is part of the mathematical proofs of, so we're going to talk about theoretical limits on the performance of these 3 types of cycles. This is at the heart of figuring out the theoretical limits of performance. In contact with one thermal reservoir. So that's just being clear on what, I've already written that a couple times, but that's the mathematical form of the Kelvin-Planck statement. Okay, so now before we can talk about the theoretical limit, we have to talk about what performance means. So performance measures of these 3 types of cycles. We're not going to get to problems today, sorry. That means I can't really assign anything new though, so that's good. So performance of cycles. So first, the power cycle. And I'm going to draw these diagrams again. So here's the system. It's in contact with a hot thermal reservoir and a cold thermal reservoir. And before I write these in, think about the directions for a power cycle. Like this stuff, you're just trying to ingrain this in your head because it's thinking about it this way is going to come up in every problem. So what's going on with the hot reservoir? Yeah, heat's going into the system, QH. What's happening at the cold reservoir? Yep, that's your Q sub C. And what's going on with work? Yep, work's being done by the system on the surroundings. So, what? So it's sort of funny, like if you're using this stuff in the first law of thermodynamics, then that W would be positive, QH would be positive, QC would be negative. But when we're talking about it in terms of these parameters, we're going to call all of these positive. Okay, so the sign depends on the usage. One thing to notice is that this is a cycle. How do you know it's a cycle? Because it's called a power cycle. And in a cycle, you can't have any buildup or loss of energy in the system because that's a property. The system has to stay the same, has to be the same at the start and end. And so this means that if you add up all the energy coming into the system, it has to equal all the energy leaving the system. QH is equal to W plus QC. Has to be the case for it to be a cycle. And we're going to use that. So now, how would you measure this is called the efficiency for a power cycle. How would you measure how well a power cycle is working? What's your ideal functioning of a power cycle? Well, you're trying to get work out of it, and you want to put as little heat in as possible. So that's the Greek letter eta, and that's the symbol for the efficiency of a power cycle. It's going to be what you get out of it divided by the energy you have to put into it. That's a perfectly intuitive calculation of how good your system is. If there wasn't any first law of thermodynamics, you could hope for infinity here, and you wouldn't have to put any energy in, and you get work out of it. If it wasn't for the Kelvin-Planck statement of the second law of thermodynamics, you'd think, okay, well, I know from conservation of energy I can't get higher than 1, but maybe I can get 1. Well, the Kelvin-Planck statement says you can't get 1 either, because you have to lose some of your energy in the exhaust. And notice that I can rewrite this. So this intuitive form, the work over the heat coming from the boiler, if I rearrange the relationship between QH and W plus QC, I can write this as QH minus QC in the numerator divided by QH in the denominator. That's from here. And I can then just rewrite that as 1 minus QC over QH. So those all have to be the same thing, and that's the performance of a power cycle. Eta. Yep. Yep. If you want an easy way to make people think you're smarter than you are, memorize a lot of names of Greek letters so you can just rattle them off fast. It's just like a tried and true, proven method. Now, a refrigeration cycle. You know what? I'm going to finish this next time. So refrigeration and heat pump. Do that next time. Any questions right now?